Hello and welcome again to my Physics Online Video Lecture Supplement series. In today's video, I'm going to begin lecture set number 3 for the Physics 2 courses, which is electric energy and electric potential. To give a quick overview, we're basically going to be looking at energy in the context of electrostatics. So it's worth recalling that we discussed potential energy in the Physics 1 courses, basically in connection with conservative forces. So potential energy is the potential for some conservative force to do work, which means, in other words, that it is the energy stored in an object by nature of the object's position with respect to the source of some force. For example, the position of an object with respect to the Earth, or the height of an object above the ground, determines how much gravitational potential energy the object has. The position of an object at the end of a spring with respect to the equilibrium position of the spring gives the potential energy of the object spring system. Potential energy is always energy stored within a system. You have to have, for example, a spring and a mass at the end of the spring, or the Earth and an object hovering somewhere above the ground or perched precariously on the edge of a cliff. In any case, recall that the amount of work done by a force in general is given by the dot product of the force with the displacement. And so that basically looks like the force times the distance traveled times the cosine of the angle, which is between the force vector and the displacement vector. And this definition applies in general for work. In the case of a conservative force, the amount of work that the force can do is determined by the potential energy, and it is ultimately not path dependent. So an object which is perched above the ground on the edge of a cliff, it doesn't matter whether the object falls straight down or whether the cliff happens to have some slope, and so the object kind of bounces along the slope in falling to get to the ground. In both cases, the conservative force in question, which is gravity, does the same amount of work, and so the object has a set amount of potential energy. So in this set of lectures, what we want to do is explore the special type of potential energy that is found in electrostatics, and also we're going to, in a future lecture, look at how this energy is actually stored. Basically, the electrostatic potential energy is based on the Coulomb force, which is itself a conservative force. Remember that gravity was a conservative force and that the Coulomb force has the same general form. The equation expressing it has the same general form as the Newton's general gravitation, Newton's universal law for gravitation. So once we have the idea of electrostatics energy in mind, we can then begin to investigate a basic component found in circuits, which is called the capacitors. Those are actually going to be the subject of the next set of lectures, but these are devices which store electrical energy. So in today's specific video, we're looking at part 1, which is basically electric potential and energy, and then in future lectures we'll look at some applications of potential energy in electrostatics, and we'll look at eventually capacitors and circuits and so on. So electric potential and electric potential energy are ultimately related. We've already talked about the concept of an electric field, and recall that the electric field is related to the force that a charged particle in the field is going to experience. So basically we express that as F equals E times Q, where Q is the charge, E is the electric field, and F is the force. We have a similar thing that we can use in terms of energy, and that similar thing is called the potential. And so the electric potential is basically the energy per unit charge that is found in an electric field. And so this is, as often is the case, easiest to calculate if we have a point charge, and we can actually apply the superposition principle to electric potential just as we did previously with electric fields. And basically what we're going to look at is some different conditions for electric potential, how to calculate it, what it does, how to get potential energy from it, etc. And then in a future, we will also look at using electric fields to figure out what's called equipotential surfaces, which are basically surfaces along which the electric potential and hence the electric potential energy for a given charge are constant, or vice versa. So let's look at all that. As stated in the overview, the only forces which have a potential energy are conservative forces. And so if the force in question is conservative, it has a potential. If it's not conservative, there is no potential that can be defined for it. Friction does not have a potential energy function because it depends upon the path taken, basically the total distance traveled to get from point A to point B. Gravity and in turn the Coulomb's force are conservative because it doesn't matter what path you take to get from point A to point B, they will still have the same total change in energy. And so the potential energy U and the work done W are relatable by this simple equation. This comes from the definition of potential energy and of work. Basically, a change in potential energy is the final potential energy minus the initial potential energy, and that's going to be equal to the amount of work that is done. So change in potential energy is equal to, magnitude-wise, the amount of work that is done on an object. And again, this is a scalar, which means it has magnitude but not direction, and therefore we don't have to worry about vectors directly when calculating it. And again, as with all types of energy, work, potential energy, kinetic energy, mechanical energy, whatever, have units of joules. And so that is, since work is force times distance, it's got to be units of force, which is newtons, times distance, which is meters, and that breaks down to kilogram meters squared per second squared. And so because Coulomb's law is similar to Newtonian gravitation in that both go like 1 over r squared and both sort of radiate outward or inward, as the case may be, from the mass or the charge in question, both are going to be conservative forces. Therefore, we can have a potential energy function that pertains to charge. So let's look at some simple case, which is work done in a uniform electric field. So what I have here is a diagram in which there is a positive test charge, that's this guy right here, which is placed in a uniform electric field. Now recall that if you have two parallel plates of charge, one positive and one negative, that you have a uniform electric field that points from the positively charged to the negatively charged plate. So if you place this test charge in between these two plates, then the force acting on the test charge should be whatever charge it has times the electric field. And so as you move this particle from one point to another, from x initial to x final, you will have some amount of work that is done on this charge by the electric field. Basically, it has got to be force times displacement, which in this case is force times x final minus x initial. Notice that it doesn't matter, in this case we're moving from point A to point B, it doesn't matter whether point A and point B are in the same exact direction as the field lines are. Point B might be down here, point A might be up here, and the only dimension that actually matters between them is x, the horizontal distance, because that's the distance which is parallel to the electric field. So the vertical distance doesn't matter. There's no work done in moving this particle from, say, right here along this dashed line to right here. No work has been done. If I move from here to right here, I do the exact same amount of work as if I move from here to here. Okay, therefore, that means that the relationship between the electric field here and the work done is given by the equation work equals charge times the x component of the electric field times the change in x position. So Q E sub x, this is the force in the x direction, times the change in x. Now, the E field is basically, again, can be pointing in some arbitrary direction, or that's equivalent to saying that x could be oriented in some arbitrary direction. What matters is the component of the field which is parallel to the displacement. And again, this can be positive or it can be negative, because Q can be positive, Q can be negative. I can go with the field, I can go against the field. So those are the sign conventions that you have to keep track of. The work done, in other words, is going to be positive in the event that the charge is positive and that it is moved along the field line. It's going to be positive if the charge is negative and moved against the field line, and so on. Actually, isn't a bad idea to construct a little table to determine whether the amount of work is sort of positive or negative. That table might look something like this. Let's say that I have with E, and I have against E, and I have Q is positive and I have Q is negative. So my table basically is going to be, is the work done positively to the particle or negatively? And basically in this case, work is positive. In this case, work is negative. In this case, work is negative. In this case, work is positive. So this is our basic sign convention in electrostatics for determining whether the amount of work done is basically increasing, let us say, the kinetic energy and therefore decreasing the potential energy, or vice versa. So let's talk about how this pertains to potential energy. As has been said a couple times already, potential energy is the potential for some conservative force to do work on an object, and that means that as you actually do work on the object, you are going to decrease the amount of potential energy that is stored in that object. So the relationship in general is that change in potential energy is equal to the opposite of the work done. So let's flip up one slide here and look again. If I allow this particle to move from point A to point B, the electric field does some amount of work on the particle, and in doing some work on the particle, this is actually a positive amount of work done. In doing this positive amount of work done, we reduce the amount of potential energy that this particle has, and conversely, we increase the amount of kinetic energy that this particle has. So to return to that table that I made a moment ago, when I have a positive amount of work, I am therefore going to have a negative change in the potential energy. And when I have a negative amount of work, I will have a positive change in the potential energy. So to fill out the rest of this table, I basically have something like this. So diagonals are same sign, I mean. So this is UE minus because it goes with a positive amount of work. This one's minus and goes with a positive work. This one's positive, it goes with a negative amount of work. This one's a negative amount of work and goes with a positive amount of stored energy. And recall that in the simple case in which we just have a single force acting on an object, that by moving the object in such a way that potential energy is increased, we're also going to be decreasing the kinetic energy. So this means that delta K is negative. This one would mean that delta K is positive. This one, delta K, is negative. This one, delta K, is positive. So now I think we have a complete set of sign conventions. Now, this equation right here, delta U is equal to negative WE, is in general valid. This side of the equation, however, is generally more valid in the specific case where you have a uniform electric field. And we can see this by analogy to the potential energy due to gravity that we've already explored in the Physics 1 courses. Here you have the case of gravity. Here you have the case of electric potential. We move from point A in this case or this case to point B in this case or this case. If you have a uniform gravitational field, that is equivalent to saying that you are, for example, near the Earth's surface where the gravitational freefall acceleration is g equals about 9.8 meters per second squared. So the change in potential energy from falling from this point to this point is given by m times g times this distance, usually represented by a delta h in the specific case of an object falling from some height. So similarly, we use q times e times delta x, or q times e times d, where d is in the direction of the E field. And this, both cases, we're assuming a constant uniform field. In the case of gravity, recall that if the field is not uniform, we have another equation that goes with this. And the same will in fact be true for electric fields. In fact, in gravity, the force went like 1 over r squared. The actual potential energy, generally speaking, went like 1 over r. So 1 over the distance away from the gravitational attractor. So let's return to our electric and gravitational potential energy analogy. There are some similarities and there are some differences. The gravitational potential energy depends linearly on an object's magnitude of mass. Okay, so this small rock has a smaller potential energy than this large rock does. Similarly, the electric potential energy depends linearly on the object's magnitude and sign of charge. So this object has twice the charge, therefore the potential energy is twice as much as this one. If this rock is twice as big as this one, twice as much mass, then the potential energy of this rock is twice the potential energy of this rock. And note, of course, that they're starting from the same height in the same gravity field. These two are starting from the same position in the same electric field. Electric potential energy actually has one bit of a modification versus gravitational potential, in that because there are signs to charge, the lowest potential energy for a positive charge is the same as the highest potential energy for a negative charge. So right here is the highest potential that these positive charges have. If I put a negative charge here, it would actually be at the lowest potential energy. And that's because the negative charge, the electric field flows from here to here. That means that the force on a negative charge is actually from right to left. And so as the particle moves from right to left, it's losing potential energy. So here's the minimum potential energy for a negative and the maximum for a positive. Here's the minimum for a positive and a maximum for a negative. Conservation of energy now looks basically the same as it has ever since we introduced it. We just have more terms that we can now add. So usually we end up subtracting one side of this from the other just to reduce the number of terms we're keeping track of. Energy conservation basically says that the difference in potential energy from whatever sources of potential energy you have, be it a spring or gravity or an electric field, plus the differences in kinetic energy, be it translational or rotational, minus any non-conservative work done to propel the object plus any non-conservative work done to dissipate energy from the object should collectively equal 0 as long as you have an isolated system. So this is the shorthand version of that. Usually we have something like a electric potential and maybe gravity. So there might be a term for these two. There's maybe not a spring attached to it, so this force may be 0. Maybe it's only translating and there's no rotation possible, so this could be 0, etc. So part of the problem solving process that we go through in solving potential energy and work and kinetic energy, basically energy conservation in general problems, is that we have to identify which of these terms we're actually going to use. So usually it's actually best to just start from scratch and write out all the terms that are relevant and then solve from there. So I want to work a few short examples with basically electric potential energy before moving on to talk a little more about electric potential. So we have a particle of known charge placed in a uniform field of known magnitude, and it moves along the field lines by a known distance. We want to know how much work is done. So work, again, is charge times electric field strength times the distance that it moves, so delta x, times the cosine of the angle between the field line and the displacement. So since it's along the field line, this term right here is actually just given by 1. E times cosine phi, by the way, is equivalent to EX. So this whole thing is equivalent to saying EX delta x, and that's regardless of what the value of phi is. So to draw this problem out, by the way, your field is basically something like this. Maybe I'll just draw a few field lines, and it has a uniform strength of E equals 1.0 times 10 to the 5th newtons per coulomb. And we're starting with our particle, which has some charge Q. So here's our particle right here. It has charge Q is equal to 1 millicoulomb, so that's 1 times 10 to the minus 3 coulombs. And it's basically being displaced from here to here. So it's moved right along this field line. This distance, delta x, 0.100 meters. So to plug all that stuff back in, we would have work equals 1.00 times 10 to the minus 3 coulombs times 1.00 times 10 to the 5 newtons per coulomb times 0.100 meters. Okay, simple. So 5 orders of magnitude minus 3 minus 1 leaves us with 1. So this would be 10 joules. Okay, now we're supposing that the particle is moving by 0.1 meters in a direction at an angle of 30 degrees with respect to the field line. So same field, same charge, all that. Now we want to know what's the work done again. All right, so here's the drawing that goes basically with that scenario. So the work done is, again, Q E delta x cosine phi. So we just solved for this part of it, which was 10 joules. The cosine of 30 degrees is going to be square root of 3 over 2. So basically the work done is going to be the square root of 3 times 5 joules. And so if you want to plug all that into your calculator, what you end up getting about 8.66 joules. So we have roughly 8.66 joules of work done on the particle in this case. Now notice that an alternative way of finding this, an alternative diagram, would have been to basically come down here and figure out what is delta x, where this term right here is really more treated as delta r. And notice that delta x is in fact delta r times the cosine of phi. So it's equivalent either way to figure out, do we want to know what the E field along this direction is, or do we want to know what the distance that it's been displaced along this direction is? Both should give us the same answer. Alright, so for our third example, we can use the work kinetic energy theorem. So work is equal to the negative of the change in potential energy, which is equal to the change in the kinetic energy. And that is basically 1/2 mv final squared minus 1/2 mv initial squared. Now, initially, the particle in question is at rest, so v initial is 0. So this basically all means that the work is equal to 1/2 times the mass times the final speed squared. So v final is twice the work over the mass with a square root. That's true in each of the two cases discussed above. So case A would correspond to short example 3.1.1, which was the phi equals 0 case. In this case, work was 10 joules, and so the final speed is going to be the square root of 2 times the work done, which was 10 joules, divided by the mass, which was 100 kilograms. So this gives us an approximate final speed of 0.4472, so 0.447 meters per second. Case B, which was short example 3.1.2, which is phi equals 30 degrees. The work done was approximately 8.66 joules, so V final is square root of 2 times 8.66 joules divided by 100 kilograms, and so the final speed is approximately 0.4162, so rounded to 3 significant figures, it's 0.416. So that is the final speed in each case. It's convenient here for us to actually give a more formal definition for the electric potential. I've kind of hinted at it at this point, so here is a formal definition. It is defined in a very similar way to the way that we defined the electric field. So the electric field was defined as the electric force per unit charge. In this case, the electric potential is the electric potential energy per unit charge. So it has units of joules per coulomb, which are sometimes called volts. In fact, that's how we usually refer to it. And so sometimes the electric potential is also called the voltage, thanks to these units of volts. And it is in fact a scalar quantity, just as the potential energy was a scalar quantity. That is to mirror the fact that the electric field was a vector quantity as the force is a vector. And here we actually have to be concerned with the sign of the charge as pertains to the potential energy. So the potential usually has a particular set value at a given point In fact, it's actually the difference that matters. More about that in a moment. The potential energy then is defined in terms of this charge, including the sign on the charge, times the potential at that point. So what about this whole defined at that point? Well, recall that as with potential energy in general, what matters is not necessarily the absolute potential energy at some point. In fact, that's usually a meaningless term, especially when talking about, for example, gravitational potential. Instead, what really matters is potential difference, or difference in gravitational potential energy. So how do we get an actual value at some point for the potential energy? Well, we begin by saying there is some point at which the potential energy is zero, and we define that point. Then we can find what the potential energy is with respect to that point. So that point is usually the ground when we're talking about gravity. And so we say, okay, the ground is where the potential energy is zero. But recall that we had an example of a person inside of a building. And in this context, we could talk about the potential energy of an object, and we could say, well, what really matters is how high is it above the floor upon which the guy is standing. Or we could talk about how high is it above the stair that he's standing on, or how high is it above the actual ground outside. And once we've made that decision, then we actually have the ability to calculate changes in potential energy, and the change in potential energy will be the same regardless of where we set our reference point. But for calculating the actual potential energy within the problem, we might want to pick a reference point first, and then that potential energy will be different depending upon what the reference point is. So in other words, the potential energy with the reference point of the stair that he's standing on is somewhat less than the potential energy of the reference point of this floor, which in turn is somewhat less than the reference point of the potential energy of the ground outside. Okay, well the same thing actually works, the same argument actually applies not only to gravity but also to electrostatic potential. So we typically can choose a reference point and call that the point at which there is zero potential. And usually we say that this is the ground. Not literally the ground of the Earth, although in actuality that works very nicely, especially when we're talking about circuits. But we pick a point that has zero potential, and then to find the potential energy at some other point, we simply ask what's the difference between the point where we've chosen to be our ground and the point where we're interested in. So what does actually matter in the end is potential difference, or sometimes called voltage drop. Delta V is the difference in potential between 2 points A and B, and that's the voltage here minus the voltage here. And we can say that this voltage here and voltage here are defined with respect to the ground. And once we've defined those, we can subtract them. We've got a potential difference, and then we don't really care whether they're defined with respect to the ground or with respect to a plate or what have you. And so this voltage drop, or this potential difference, is actually the change in potential energy per unit charge between points B and A. And again, if you have a uniform electric field, you can get that by taking the electric field strength and multiplying by the distance that the particle has moved along the electric field line. So sometimes the SI unit that we use for the electric field is actually volts per meter rather than newtons per coulomb. Okay, the electric potential created by a point charge of magnitude Q is going to look very similar to the potential energy that we have for a point mass at some position r away from where we're interested in, save that A, we're talking about potential versus potential energy. So the only thing that matters is the actual charge of the source that we're defining a potential energy with respect to. And basically, that we're talking charge rather than mass. So there, you could think of a gravitational potential as having the form G times m over r for a point mass. So for a point charge, V is the Coulomb constant times the charge divided by the distance from the charge. And again, we can get that fairly easily by saying that the electric field is KEQ over r squared, and we are some distance r away. So if we move from that point to a distance r away, we've moved through a distance r. We have to multiply by r, and hence your r squared times r gives you this 1 over r term. And so sometimes the way that we actually define a zero, the ground, is to pick a point that is infinitely far away, which basically means anywhere infinitely far away. And we call that the location where the potential is zero. It's worth noting here that we can relate the electric field strength then to the voltage drop by using that the electric field strength is the voltage drop per unit length that we have to travel to get a given voltage drop. So if it takes 1 meter to get a voltage drop of 1 volt, then the electric field, if it's uniform, is 1 volt per meter. To help you sort of visualize what happens when you have a point particle, I've pulled a plot of both the electric field strength and the electric potential as a function of the distance away from a given point charge, what these two things look like. So E is KEQ over r squared, V is KEQ over r, where Q is the charge on the point source that we're finding potentials from and finding electric fields due to. So this, you can see that both, of course, decrease as your distance increases. This one like 1 over r, this one like 1 over r squared. One thing that could be said here is if you want to find V, you're basically finding an area under the E curve, the E versus R curve, just as we did with gravity and just as we did with springs in the Physics 1 class. Alright, so we can apply the superposition principle to electric potential just as we were able to apply it to electric fields. And the thing here is that it's actually kind of easier to apply with electric potential than with electric fields, because with electric fields, your superposition principle requires that you do a vector sum, but with potential, you actually only have to do a scalar sum. So figure out what the scalar potential due to a bunch of charges is, add them together. Now you have what the total scalar potential or total electrical potential at point P is due to this configuration of charges. So as a short example, what happens if you have two charges of equal magnitude placed some distance apart, and we want to find what the electric potential is directly between them. Alright, so we're looking for the potential at this point, midway between these two particles given some charge. So to get the total potential, we use V is equal to V1 plus V2. And again, this is not a scalar. As it turns out, in this case, this is going to be V1 is equal to V2. But we'll go ahead and calculate the normal way by calculating V1 and calculating V2. You would have KE times Q1 over R1 plus KE Q2 over R2. Okay, and that is going to be equal to basically KE times Q1 would be 1 by 10 to the minus 3 coulombs divided by R1, which is 0.5000 meters, And then same thing here, 1.00 times 10 to the minus 3 coulombs divided by 0.5000 meters. Ke, recall, is the Coulomb's constant, so it has a value of about 8.98, whoops, dyslexic moment, 8.98 times 10 to the 9 Newton meters squared per Coulomb squared. So we can do this calculation by noting that this is basically 2 times 10 to the minus 3 plus another 2 times 10 to the minus 3, so that's 4 times 10 to the minus 3. So that times 8.98 gives us 35.92. So basically you end up with V is equal to 3.59 times 10 to the, let's see here, 7. So 7 volts. And there is your potential at this point. Now suppose that I move this point from here over to another point that is maybe located right here, which is only 0.25 meters away from this one and 0.75 meters away from this one. Note that this point and the point right here will actually be equal potential points. They'll have the same potential at both. In that case, we repeat all of this, but now we end up with Ke times 1.00 by 10 to the minus 3 coulombs over 0.25 meters plus 1.00 times 10 to the minus 3 coulombs over 0.75 meters. So if we plug all that into our calculator, what we end up getting is that the total voltage in this case, the total potential, is about 4.789, so 4.79 times 10 to the 7 volts. So we have a different voltage here than we have here. In fact, this point right here is going to turn out to be the minimum potential that we can get between, as long as it's in a straight line between this point and this point. This is the minimum. And so if you were to place either an electron or a proton here, this becomes an equilibrium point for both. And if it's displaced a little bit, then in the case of the proton, it'll actually be repelled to get back here. And so this is more or less a stable equilibrium, and you'd have an oscillation about this point. If it's an electron, this is an unstable equilibrium, and a slight displacement will cause it to accelerate towards one or the other of these charged particles. So since we defined the electric potential to be the potential energy per unit charge, it therefore follows that if you know what the electric potential is at a given point, and you have a known amount of charge, you also know how much potential energy is in that charge by nature of being at that point. So again, we can define this with respect to a ground potential, as in a circuit, or with respect to a potential that's infinitely far away. Those are our two versions of potential energy equals 0. And so if you want to get the potential energy of a charge Q2 due to a potential that's generated by a charge Q1 for 2-point charges, you would use Q2 times V1, which is equal to Ke Q1 Q2 over R12, where R12 is in fact the distance between the two charges. Note that this is not R12, this is R12. So it is the distance between two given charges. So here's charge 1. It creates a potential V1 at point P. We place charge 2 at point P. Here is what the potential energy that charge 2 will have is. And as you move the two charges closer together, this potential and therefore the potential energy are going to be increasing. By the way, since electric charge times electric potential gives potential energy, we actually have a new unit that we can define for energy. And this new unit is called the electron volt. It's abbreviated EV. So basically what it is the amount of electric potential energy which is gained by an electron, or for that matter a proton, anything with a charge of E, when it's been accelerated across 1 volt of potential difference. And what it's actually useful for, there's actually quite a few things that it's useful for. For one thing, we often use EVs as the unit of energy when talking about small particles like an electron or a proton. For that matter, we can use it to talk about energy in a single wave packet of electromagnetic radiation, in other words, a photon. And basically what you need to know is what's the conversion factor to get from EV to joule or vice versa. 1 volt is a joule per coulomb, and an electron has 1.6 times 10 to the minus 19 coulombs. So our conversion factor is basically that 1 EV is the same as 1.6 times 10 to the minus 19 joules. So that's how you get from a macroscopic energy to a microscopic energy, or vice versa. we take a small conducting sphere with a given charge and a given mass, and it's placed in an electric field and a gravitational field. And the gravitational field is for the Earth's surface. The electric field is uniform and perpendicular to the gravitational field, and it has some given strength. And what we want to know is what will be this particle's position after 1.0 seconds if it's initially at x initial equals 0. So let's start off by drawing ourselves a diagram, which is always kind of a good strategy. Here is the particle. It has a mass of m equals 1.00 kilograms. It has a charge of Q equals 1 millicoulomb, which is 1 times 10 to the minus 3 coulombs. Its position will be here. I'll mark off position using, let's say, blue. So x initial is equal to 0. And let's see here. We have a gravitational field, which is like this. G straight down. This is as straight as you're going to get out of my drawing on this tablet that I work with. So live with it. Then we also have in the same vicinity, this is G is 9.8 meters per second squared. Let's call downward the negative j hat direction. In other words, it's in the y direction. And we also in the same place have an electric field, which is perpendicular to the gravity field. So that's like this. Merry Christmas, I guess. And so we have an electric field going here. E is equal to, we had 5.0 times 10 to the 6th newtons per coulomb. And this is in the x direction, or I hat. And so we're going to move the particle through 1 second along this way and along this way. We'll say that here's x final. So x final, this may not, x and y may not be to scale with each other. And what we want to know is where is x final. I'm going to represent this as actually being x I hat, or x along the horizontal direction, plus y j hat, or y along the vertical direction. So now we do a little math. Recall from kinematics. So kinematics says if you have a constant acceleration, so a is constant, then our final position, which I am using x to represent, x final is 1/2 of a t squared plus v initial times t plus x initial. And we were told that this thing is initially at rest, or at least we aren't given any information to the contrary. So this term right here is 0. We're told that this term right here is 0. So it's really this part right here that we're worried about. How do you get the acceleration? Well, acceleration is force per unit mass. So in the context of this, we basically have m times g plus q times e over m. And so in vector form, what this looks like is basically q over m times e in the I hat direction. And m over m cancels, so we're left with g in the negative j hat direction. So negative g j hat. Okay, so our final position, therefore, is 1/2 of q over m e I hat minus g j hat times t squared. Now t was given. T equals 1.0 seconds is a given. So what this gives us is that the final position, so Q was given up here, M is given up here. We can plug numbers in other words. This is 1/2 of, let's see, Q is 1.00 times 10 to the minus 3 coulombs divided by 1.00 kilograms times 5.0 by 10 to the 6 newtons per coulomb I hat minus 9.81 meters per second, 9.80 meters per second squared j hat times 1.0 seconds squared. So our final position, therefore, is going to be given by, let's see, that's 2.5 times 10 to the minus 3 plus 6 is 3. These units all work out to give us meters in the I hat direction, plus, minus 4.90 meters in the j hat direction. So if we wanted to express this as just a Cartesian coordinate, it would be 2500 meters, comma, negative 4.9 meters. Okay, so we've solved part A of the question. So we've just answered part A. Part B, how fast will it be moving at this time if it's initially at rest? We could actually use forces to get the answer to this, or we can use conservation of energy. Since these are supposed to be energy questions, I'm going to use conservation of energy to solve it. And actually the way that we do this is we can use that work is change in potential energy, is negative change in potential energy, which is equal to change in kinetic energy, which in this case is 1/2 mv squared, or mv final squared. Work, of course, is going to be force times distance. So this is equal to basically F dot delta x, which in this case looks like Q times E plus M times G dotted with the difference between x final and x initial. Since this term is actually 0, we can do like that. Alright, so basically we have that Q times E times delta of the x term plus M times G times delta of the y term is actually equal to 1/2 times m times v final squared. So we can divide out an m like so. So what we end up getting is that the final speed should be equal to 2q e over m times delta x plus 2 times g delta y with a square root over all of it. So 2 times q times e over m. We've already kind of done the whole q over m times e. So this term right here has a value of basically 5 times 10 to the 3. That's being multiplied by 2500. This term right here has a value of basically 9.8 times 4.9. Okay, multiply both of those by 2, add them together, take a square root. We can see, by the way, that this term is virtually not going to matter. Just for fun, I'll calculate it without this term, and then I'll calculate it with this term. You get 5,000.0096. So without paying attention to significant figures, 5,000.0096 meters per second. And if you ignore gravity here, you have 25 million, the square root of which is 5,000. So gravity is very negligible in this problem. The particle practically moves in a straight line along the E field. Okay, the last part of this example is what is the potential difference delta V across which the particle has moved? So to get that, we can use that delta V is the same as U sub E over Q, which is, this is change in potential energy over Q, and that is going to be the work divided by Q, or negative times the work over Q. This doesn't necessarily need to be the potential due only to the electric. We could include gravitational potential and say that this is the total potential difference, but the gravitational potential is so small that we can practically ignore it, because this is basically going to be Q times E times delta X over Q plus M times G times delta Y over Q. And this term is so much smaller than the other term that we can treat it as if it is 0. And so delta V, the potential difference across which this thing has passed, is going to be negative 1 times 10 to the minus 3 coulombs divided again by 1 times 10 to the minus 3 coulombs. These two should be canceled. Times 5 by 10 to the 6th newtons per coulomb times this distance 2,500 meters, so 2.5 times 10 to the 3 meters. So if we multiply all that together, we get that the potential difference across which it has moved is 1.25 times 10 to the 10 volts, and that's actually a negative because, again, the electric field has done work on this particle, so it has in fact lost potential energy and therefore is sitting at a lower potential than what it started at. Alright, for our next example, we consider a dipole, which is a pair of charges that have equal magnitude and opposite signs. This, by the way, is the electric potential contour map for that. Basically, a contour map means that anything that's at the same height here has effectively the same potential. And so our question is, we're going to take the zero potential or ground to be infinitely far away from the pair. Out this way, keep going, keep going, keep going. And what we want to know is what is the potential relative to that at several locations. One location is right here midway between the two charges. One of those locations is 1 nanometer from the negative charge and 2 from the positive charge. So that would actually be equivalent to looking over here somewhere. And then similarly, we want to see what happens when we are 1 nanometer from both charges, which would be like over here, for example. So let's go ahead and draw what that looks like over here in a simpler sketch. Basically, we have charge number 1. This is the plus 1 nanocoulomb, or 1 times 10 to the minus 9 coulombs. Here is charge number 2, Q2. This is minus 1.00 times 10 to the minus 9 coulombs. They are separated by a distance of r, 1, 2, which is 1 nanometer. So 1 times 10 to the minus 9 meters. And where is it that we want to find our potentials? I'll go ahead and mark it with a set of x's. So one point would be right here. At this point, we basically are 5 times 10 to the minus 10 meters away from each charge. I'm dropping some significant figures, obviously, from that first one. So that would be here. That's position number 1. The second place that we're supposed to find, B, 1 nanometer from the negative and 2 from the positive charge. So position number 2 is actually right here. So this right here would be R, we'll call this R2B. This is R2A. And so this is 1 times 10 to the minus 9 meters. And here would be R1B, and that's 2 times 10 to the minus 9 meters. Okay, and then our last position is supposed to be 1 nanometer away from each. So that would basically be located, for example, right here. So R1C is 1 times 10 to the minus 9 meters, and R2C is 1 times 10 to the minus 9 meters. So we're finding the potential at each of these points in turn. So for all of them, the approach that we take is V is equal to V1 plus V2. And so that is KE times Q1 over R1 plus KE times Q2 over R2. And so now let's do this for each of these cases in turn. So for case A, we have R1 is equal to R2 is equal to 5.00 times 10 to the minus 10 meters. So that means that V is going to be KE times Q1 was plus 1.00 times 10 to the minus 9 coulombs over 5 times 10 to the minus 10 meters, and then that's minus 1.00 times 10 to the minus 9 coulombs over 5.00 times 10 to the minus 10 meters. So obviously this and this cancel, and so for part A, we'll call this VA is equal to 0. So the potential midway between the two is equal to the potential at infinity, so we can actually use this as our ground if we want, as our equilibrium point, or excuse me, as our zero potential point. All right, for B, what this looks like is that VB is KE times plus 1.00 times 10 to the minus 9 coulombs divided by 2.00 times 10 to the minus 9 meters minus 1.00 times 10 to the minus 9 coulombs over 1.00 times 10 to the minus 10 meters. Okay, so this basically is a half plus 1/2 minus 1 times KE. So basically this one right here is going to be VB is approximately, remember that KE is 8.98 times 10 to the 9 Newton meters squared per coulomb squared. So basically what this all gets, because these are in coulombs, these are in meters, we're going to end up in volts, and we can basically just divide this number by 2. So it should be negative of, I guess this would be 4.99 times 10 to the 9 volts. So that's what the potential is if we are on the 1 nanometer away from the negative and 2 from the positive. Of course, if you flip to the other side so that you're 1 nanometer from the positive and 2 from the negative, then this is just a positive 4.99 times 10 to the 9 volts. Okay, for part C, we are now looking at KE times plus 1.00 times 10 to the minus 9 coulombs divided by 1.00 times 10 to the minus 9 meters. And then from that we subtract 1.00 times 10 to the minus 9 coulombs divided by 1.00 times 10 to the minus 9 meters, because now we are the same distance away from both of them. That's the equilateral triangle case. And again, we see that these two cancel. So VC is once again 0. The implication of this is that any point which exists an equal distance between the two charges should have a potential of 0. So that means that if we were to try and figure out, so here is Q1 and here is Q2, any point along this line that is an equal distance r from both of these, R1, R2, R1 equals R2, the potential anywhere on this line should be 0. So this is what's sometimes called an equipotential line. And in fact, if we were to expand this into 3 dimensions, this line becomes a plane. And so it's actually an equipotential surface or an equipotential plane. Anywhere on the plane where the plane is coming out of and going into the screen and is, vertical midway between these two should have the same potential of 0. So that's all for today's video. I understand it's been kind of a longer video, so this is actually sort of 2 very long videos in a row. Happily, a lot of the length in both of them has been examples, so that should make a lot of people happy, since a lot of people actually want to have more and more difficult examples. So more of the examples, more of the difficult examples. In any case, that's all for today's video, and I hope that you found this to be helpful in watching through both the lecture and the examples that go with the lecture. And thanks for watching this video.